today will be in characteristic D. Throughout. One of the big result from lecture 1 was Kunz's theorem that said for polynomial ring over a perfect field, or more generally a F-finite regular local ring. Let me stick with that version. The ring R became a free module by the restriction of scalars action. Okay, and we also use this terminology notation FE lower star R to prime us into the fact that we were thinking of R by that module structure. FE lower star R was a free module under this structure. In lecture 2, we got what I think of as a pretty concrete payoff for this, right? We use this to get this this trick that says I can get a little bit of wiggle room to show that things are ring elements are inside of ideals, and this wiggle room is useful, right? So put those two things together. The fact that R was a free R module by restriction of scalars through Frobenius is useful. Okay, right, that's the two implications put together. I also, right, so that Kunz's theorem also has this converse, right? This only happens when R is regular or polynomial, whatever, right? So not every ring is like so, but we can ask for weakenings of this hypothesis that are still useful in similar ways. And that's what the general notion of F singularities is about. Let me do a heading before a definition. So this is a general term that means, and so the singularities half is saying we're maybe considering rings that are not regular or are different from polynomial rings in substantial ways. F is for Frobenius, and the general idea is that we're going to weaken the other side of Kunz's theorem and still be able to do some of the things that we liked in the case of regular rings. So let's waste no time and collect an F singularity. We'll say the ring R is F split if there is an R module homomorphism from restriction of scalars R back to R, and this is going the opposite direction for Frobenius, that sends the doppelganger of 1 to 1. Okay. Let's go back to our favorite example, polynomial ring over a perfect field. Then we know that F lower star S is free with an explicit basis. With doppelgangers and monomials that look like this. Okay. Because this is free, we're free to map these by an S linear map however we like. Okay. I can make an S linear, there's one and only one S linear map that does this. And okay, actually, I don't really care what happened to the other ones in particular. This goes into this. This is a map that witnesses that S is F split. We also saw what we needed to see in the exercises to convince ourselves the definition of F split applies to this ring. This was the conclusion of one of the exercises. And this is, let me say, isomorphic and as our modules. So for basically the same reason as what's happening here, I can do whatever I want on the different pieces of the direct sum. For example, send all this stuff to 0. And this is free to be sent to 1. That's what the definition looks like. And the point is that these things, these definitions, is that some of the good stuff that happened before still happens. Let's look at the first good thing that we saw. Assertions in the F split ring is reduced. Again, a reminder of the first thing that we saw, other than the definition. Take one of those things that we get from the definition, one of these maps. Okay, sure. It's enough room. Okay, let's apply F and then phi to an element. Okay. Again, I'm thinking of Frobenius as decorated. And here's the payoff, right? Now we're happy that we have a new name for this guy. All right. Remember this F star gadget, things look Frobenius larger on the inside than on the outside. So if I pull something out, I can do so as long as it has a pth root. Okay. All right. What was the only condition that we haven't really explored yet? R linear. Okay. R times 1. Yeah. Okie dokie. Okay. Well, all right. That means that F has to be injective, right? So. For beating S map, definitely to be injective. Good. There are some minor variations on, moderately minor variations on the definition that give you the same thing. R's F split. Same thing, but any E. Same thing, but there exists an E. Also, E and an element. Such that is part of the dittos. So if I sent anybody's doppelganger to 1. Some of these implications are tautologies. The others you'll work through in the exercises. Okay. Now, prove this. Let me instead tie this together with Tuesday's lectures. If R is F split, then every ideal is Frobenius closed, in the sense that the Frobenius closure of the ideal is no bigger. Okay. Of course, step 1 is to recall what this definition was, so let's do that. Continue. Right. And let's remember that this containment, nothing much is going on here. Right? This was generated by all the elements that were the powers of elements of the ideal. Good. Okay, so we need to show that somebody in the IF was in original Y. Okay. And actually, before we write down the first step, we're going to try to use the fact that we are F split. I want to view this containment in orange, right? So the first step of this is going to say, I want to think of this as happening on the target side of Frobenius, and then be able to map things back, right? That's how we're going to use the fact that we're F split. Okay. So nothing happened in this step. Just I'm viewing this in the other copy in in a copy of R that I'm thinking of as being mapped to by some copy of R by the Frobenius, different copy of the Frobenius. Good. Okay. All right. There's a rule for this. And there was an exercise about this, which is basically just the fancy version of this rule. Yeah. Oops. Yep. Yes. I don't even need parentheses anymore. Very good. Okay. Oh, yeah, let's just check that out. Kind of undoing our proof of that exercise, but whatever. Okay, good. All right. Now we'll map back. Okay. And you'll notice the fact that we'll use number 2, right, that equivalence. Okay. We'll apply to this. So then R linear. R linear. Oh, this is an I. Right. That's what we wanted to see. Yeah. Yep. Questions about this so far? Yes. Converse of, oh yeah, very good. So yes, at least under, yeah, let me say at least under mild conditions and leave it vague like that. Yes, it's a good question, and we'll bookmark this question and actually circle back to this in a little bit. Great. Yeah, yeah. Every ideal for being is closed. Then I'm at split under mild conditions, approximately Gorenstein, whatever that means. And good, very good. Other questions? Cool. It's nice to be able to tell if a ring is F-split, and there's a very useful criterion for this. So let's take an F-finite regular or local ring, and let's also be concrete. Localization of a polynomial ring at the maximum ideal generated by the variables. Okay. So if you're not familiar with these localizations, this what this guy is discussed in the lecture one notes, and I can talk about it more in the problem session if anyone's. Oh, K. Oh, yeah. I guess I didn't say K was perfect. Yeah. Yeah, good point. I assumed something. I remembered assuming something about K at the beginning, but not this. Here, let's make it here. But sorry. Oh, good. Okay. Okay. To show that. Okay. It's also in problem set 1. Very good. All right. Let I be an ideal. Oops. R is not a thing yet. Okay. Prepare this for an if and only if. Then this property of the quotient ring boils down to some sort of very concrete containment of ideals. Yeah. Yep. Thanks. Yeah. Good. Very concrete, not containment of ideals inside of this ring here. This is the same colon from lecture 1. Oh, yeah. That's right. Yeah. It is. Yes. So, okay. So we saw it in this special case. Okay, this isn't local, but from basically the same sort of games that we played here in the local case, it'll follow up. If I have enough time, I'll also prove something a bit stronger as well, that directly in these regards. But yes, good. And I want to emphasize the case where I is a principal ideal. Right, then this colon ideal is also principal, and and I just need the generator to stay out. Okay. Good. Yeah. So there'll be exercises using this in the problem set. So maybe I'll, just to make sure I save time for other stuff, avoid slowing myself down too much with an example here. Let me just make the vague comment that one can actually use this. And the other thing we know, it's been erased, but the other thing we know about F-split rings to prove something useful. It's often not easy when confronted with a random ideal to determine whether it's a radical ideal or not. One can actually use Fetter's criterion to help you do this. Generally, Fetter's criterion plus other wits. Let me leave this like this, because I have another application in mind too. Any other questions right now? Yeah. No, please, yeah. Maybe, I don't know.
A ring which satisfies these hypotheses.
Sure.
That S mod I is F split is
Oh, no. So F split doesn't imply Cohen-Macaulay in general.
Just does it go the other way? Because I was thinking about like taking it.
Yeah. Yeah. So no, F split sort of, yeah. So it certainly has the feel of things like Cohen-Macaulayness and takes you sort of in that direction, but it is not comparable one way or the other. And maybe that's a good reason to pose some stronger definitions. Yeah. Very good. Yeah. So maybe let's do that. Okay, good. So F split was good, but we already know we want better. This sounds pretty strong. All right, so let's see what's happening here. This is certainly supposed to look a little bit like F split in the sense that this is about R linear maps from Frobenius restriction of scalars guy back to R. And we also want these to be surjective maps, splittings of some sort. What's the new element here? C, obviously. I guess there's E in comparison to the original definition, but we know from the lemma this is not the exciting new thing. C is the exciting new thing. Okay. So the point is now I can send anybody's doppelganger back to 1, but not immediately. I might have to go to higher and higher Frobenius restriction of scalars to do so. Okay. That's what's going on here. I can send anybody back to 1 eventually. No, please, yes.
In the case that R is reduced, that this is just after.
Right. Well, so this is going to end up showing that you don't have embedded primes anyways. So it's going to be a consequence of the definition. But I need to at least start off with the flexibility in the with this flexibility in the definition to recover that. Okay. Yeah, so that's what's happening. It's just a technical reason. Yeah. And well, it's not just, yeah, it's no, I mean, I need this to recover the fact that there were that I didn't have embedded primes. Yeah. I mean, yeah. Okay. Yeah. Yes and no. Yeah. Okay. Good. Yeah. Good. But now I'm gonna undo all of this discussion and say if R is a domain, then is just C is not equal to 0. And maybe we'll undo this discussion even more in the problem set. All right. Good. We see the parallels. Not yet. Okay, now we see the parallels. Okay. Let's flip it up. We want to do it pretty similar to this one. Let's do it. Okay. This is a good reason to do it. We get to remember the definition. Okay, good. We have to remember the definition of tight closure. Things look kind of similar. Well, let's see what happens. Okay. So we always have this containment, and we just need to show the other one. C with the same fine print. Good. I want to think of this as as taking place in somewhere that's more Frobenius than where I started off life. We're getting pretty good at this rule by now. Good. And that one. I don't want to write this out. Let's just say it out loud. Okay. I possess a C, so there exists an E and a phi. Okay. And just give me that phi, a phi that does all that stuff. Okay. Okay. And apply it to what we've just learned. Okay, I'll combine a few of the steps we did last time to say we can just pull out the ideal here, right? We're good. Basically the same argument with different quantifiers or more quantifiers. Oh, actually, sorry, let me do something before this. Yeah. I'll do it later. So don't even have to erase it. Cool. Should have said this when I first put down the definition, but strongly F regular implies F split. Take C equals 1. Not in any prime at all. Okay. Good. Good. So R is an F finite regular local ring, then R is strongly F regular, and in particular F split. So this is a consequence of Kunz's theorem. We have to just use a couple of small other facts from commutative algebra 1. Call it S, whatever. These hypotheses were enough to say that Euler star is a free R module. So. So you might object to how explicit this is, but whatever. If if the images of my set forms a basis for R on m to the bracket p to the e, then fe lower star b forms a basis. Actually, let me write it like this. Forms a basis for fe lower star of r mod m to the bracket p to the e. Then fe lower star b forms a free basis for fe lower star r. This is basically Nakayama's lemma. Comes from Nakayama's lemma. Good. And so now, maybe I'll call this more of a sketch. I'll let you work through the rest of the details. Then, given some element c, I can find some e such that I'm part of this basis, then I'm part of a free basis for fe lower star r, and I can be sent back to 1. Let me leave that like so for now. You can fill in the details in the problem session. Because I want to include one other notable class of strongly F-regular rings. There is an analog of Feder's criterion that one can use to test for strong F-regularity called Glass-Brenner's criterion. I want to talk about a different source of strongly F-regular rings instead. Given an inclusion of rings, we say that R is a direct summand of S if there is an R linear map that sends 1 back to 1. This is generalizing what happened for our definition of F split. R is a direct summand of F lower star R is another way of saying what it means to be F split. Good. But this can happen in ways that don't look very Frobenius at all. So so give me one of those things. I'm only saying domain here to be lazy, so don't ask about this. Then I can use this relationship to bring these good properties from S down to R. Okay. And Given the choice between an example and an application, I'm going to do an application. I have to make that choice. Um, so this has something to say about magic squares. What is a magic square? Something like this. Okay. So this is a 4 by 4 magic square with row sum. Let's see, 24, 28, 29, 33. Good. Good. All of the rows add up to the same number. All of the columns add up to the same number. That's what it means to be a magic square. And while all of these were strictly positive, I will allow 0 as an entry in a magic square. Okay. So fix a size, t by t, and let the row sum, n, vary. One can ask how many magic squares there are. I'm not going to give you a formula, but I'm going to describe the behavior of a formula, or how formulas may behave. Yes.
For this counting, are you like counting up to permutation of columns or?
No, literal. Yep, literal count. Yeah, good. Okay. This thing is a function. It is a non-negative integer valued function. And the assertion is that for the values that make any sense and is greater than or equal to 0, this travels as a polynomial, starting immediately at n equals 0. Good. So let me outline the proof. And t equals 3 just to, so I don't have, just to be lazy. Okay. For every magic square, I will assign a magic monomial. Okay. There are many monomials that are not magic. Suffices to count the ones that are. One checks that the vector space spanned by the magic monomials is a subring, and it is a graded ring, and the vector space dimension in degree t times n is the number of magic monomials corresponding to row sum n. Sorry, can I take? Okay, thank you. Okay, this step is completely elementary. This step is not quite completely elementary. This is the one and only step, the ones I'm going to list, that requires any combinatorics or maybe more convex geometry. So this is a consequence of some theorem about the cone generated by permutation matrices. And ours generated by the magic monomials whose row sum is 1. Okay. So, okay, divide the degrees by t, who cares? R is a standard graded algebra. So it's eventually, this MTN is eventually going to agree with a polynomial. The theorem is telling us something much more interesting, though. This step is also not so hard. One of the exercises. R is a direct summit of S. So R is strongly F regular. Okay, and this will just be in very loose, broad strokes. Okay. One can use the strong F regularity property to show that certain graded parts of local cohomology modules vanish, whatever those are. We'll learn more about it this afternoon. Which will imply vanishing of certain Betty numbers. Going to be the content or part of the content of Friday's afternoon lectures. Okay. And good enough understanding of the Betty table is good enough to say that the Hilbert function is a polynomial from the very beginning. And that's the content of the theorem. All right, sorry for going over.